Yes, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. I'd like to first appreciate and welcome our members to my channel. Kindly go to YouTube and search Ernest Sciences and Mathematics TV channel. Subscribe and engage us in the comment section. And also, I would like to encourage our members to be checking description boxes of various videos that we upload. I normally put a link of a playlist of videos which are similar to topics specifically under discussion. Now, in our discussion today, I'm going to look at the harmonic oscillator. And at the end of our discussion, of course, I'm going to show us one of the ways in which we can represent this aspect of energy of harmonic oscillator in terms of a partition function. Now, we're going to, of course, derive this using a specific relationship, whereby we say that one of the characteristics of harmonic oscillator is that the process what we refer to as vibrational frequency, which is given in terms of omega. So therefore, we're going to have this one as a vibrational frequency given in terms of omega, and then we're going to see that we have what we refer to as a force constant. And if we're going to consider the diatomic molecule, then therefore we're going to see that this is a force constant of the bond. And we had talked about this specific aspect of a bond in our illustration of the heteroatomic or the heteronuclear diatomic molecule, which we had considered for this specific case, having those two atoms represented by the first atom with a mass m1 and another atom with a mass m2, and they are separated by this specific distance of a bond length, which is r. And therefore, we had said that basically for us to describe this specific aspect of the diatomic molecule, we're going to use two aspects of the moment of inertia and this specific distance from the center of mass, which can be given in terms of R1 and R2. And assuming that this basically is the position for the center of mass, and therefore the center of mass, the distance between these specific molecules and the center of mass, and of course the moment of inertia, therefore are going to assist us describe this specific rotational aspect. And of course for vibrational aspect as well, we are going to look at a unique case which is going to assist us describe. Now in this case, then therefore we're going to consider an harmonic oscillator, which I've mentioned that it has got this specific relationship between the vibrational frequency, the force constant of bond for that diatomic molecule, and of course we're going to look at as well the concept of reduced mass. Now from the specific illustration I've given here for the diatomic molecule with the two specific heteroatomic, of course, diatomic molecule, I'd say that this one possesses mass of 1 and mass 2. Therefore, we're going to use the reduced mass to describe this specific system, whereby we're going to have m1, m2, all over m1 plus m2 representing. This specific equation is going to represent what we refer to as reduced mass. And this is going to assist us with one specific property of the moment of inertia, which I said is going to assist us to describe one of the aspects of which is a rotational aspect of this specific atom. Now in this case, the reduced mass as well is going to play a vital role for us describing this specific aspect of the molar vibrational partition function of the diatomic molecule using the concept of harmonic oscillator. So we're going to have this particular aspect of this symbol meaning reduced. So reduced mass. And therefore, there's a relationship between omega k and reduced mass, and this can be given in terms of omega is equivalent to 1 over 2 pi, and then we're going to have the root over k all over reduced mass. So therefore, these specific properties which are going to assist us to describe the harmonic oscillator have a general relationship which can be given in terms of this. So I'm going to put this one at this side so that we, in case we come across it, then therefore we're going to use it appropriately. So we have k over reduced mass as the relationship that exists between this specific aspect of a diatomic molecular or a diatomic molecule being considered as an harmonic oscillator. So if we go ahead and therefore we're going to look at this specific thermodynamic properties, which of course I said can be given in terms of the partition function. Now in this case, we're going to consider the energy of an harmonic oscillator, which of course are going to be derived from Schrodinger's equation of an harmonic oscillator, that is going to give us a unique set of equally spaced and singly degenerate levels. And of course, for the from the Schrodinger's equation, we're going to have the allowed energies given in terms of U n V, which represents the vibrational modes of this, or the vibrational aspect of energy of this harmonic oscillator. And this is going to be in terms of n plus a half into h omega given as such. So in this case, we're going to see that there's an aspect of n being included, and this is n is going to represent the vibrational quantum number. So this is going to be vibrational quantum number, and this is going to range between the values of 0, 1, and this is going to go on as such. Therefore, this is a general equation from Schrodinger's equation of a description of the energies of this allowed energies of this specific harmonic oscillator. Now, in this case, we're going to see that we can represent this aspect of an harmonic oscillator in terms of vibrational energy levels, and this is going to be given in terms of a potential energy curve, which I'm perhaps going to show in this specific case, whereby we're going to have this one as our lowest part, and this just going to give a general illustration for this energy curve. And of course, this is going to be a description of U being given as such, and then we're going to have this one as values for the different values of n, which we have said these are going to represent vibrational quantum numbers. So these are going to ascend in this specific order. And then we're going to have this one representing the values of n, which is a quantum, the vibrational quantum numbers. So the value of n is equals to 0, 1, 2, 3, 4, 5. And then for these various ranges of these specific quantum numbers, we're going to have the energies described in terms of a half HW. So this is according to this specific formula. Therefore, we're going to have this vibrational energy being given in terms of a substitution for n for 0 is going to give us a half HW given as such, and for the value of n is equivalent to 1, that's going to go in that specific order for 3 over 2 HW, and then we're going to have 5 over 2 HW, and that is going to ascend in that order, 7 over 2 HW, then we're going to have 9 over 2 HW, and then lastly we're going to have 11 over 2 HW given in that specific order. Now, from this potential energy curve, we can of course see that basically at the ground level, whereby we're going to have this value of the vibrational quantum number equivalent to 0, we're going to have the value of U n V equivalent to a half HW. This basically represents a level at which we're going to have this particular 0 potential energy. And of course, we're going to see that this particular level, as I've mentioned, the value of the number of n is going to be 0. Now, as we said, if we consider this particular system of course, particles as we had discussed from the Einstein-Sparks uncertainty principle, therefore it will be difficult for us to pinpoint the position of this specific particle, perhaps in terms of a molecule at any particular level. So at this point, then, therefore, we're going to have this lowest part of this specific energy level equivalent to 0, and therefore we're going to have the value of this energy represented as a half HW given as such. Now we're going to consider other specific levels of this specific harmonic oscillator, but from this particular discussion that we have had, therefore, I'm going to have a general case of this specific representation, which is going to assist us transit into partition quantum partition function, which is going to be assisting us represent the various, of course, levels, thermally accessible levels of this representation for harmonic oscillator. Now, in this case, therefore, I'm going to use the general illustration for a partition function, which we are given in terms of Q. Therefore, this is going to be a Q vibrational. Therefore, I'm just going to reserve that and maybe do away with it in case we don't need it. So we're going to have this specific Q vibrational given in terms of this energy, whereby we're going to have it as a summation of the value of n from 0 to infinity. We say that this value for 0 is going to, n which is a vibrational quantum number, is going to range from 0 to infinity. and then we're going to have this one given in terms of the exponent of this negative value of n plus a half hw, or this is omega and not w, representing the vibrational frequency, and then we're going to have that one divided by k bt. Basically, this is a substitution from the general partition function we had given, whereby we're going to substitute this vibrational energy which was given in terms of u, v, and then this is n times, whereby the n is going to range between these values of 0 and infinity. So for the general illustration, then therefore we're going to have this specific representation for a molecular vibrational partition function through this process of substitution. Of course, we had mentioned the concept of a quantum aspect insofar as summation and the integration is concerned. And we are going to see that generally, if we are going to consider harmonic oscillator, the separation between these specific, levels is going to be elaborate. And then, therefore, we are going to consider the two states, as we said, of using the concept of vibrational temperature. And in this case, for an harmonic oscillator, we're going to see that these spaces are going to be relatively large. And therefore, we're going to consider the concept of summation in representing this specific aspect of the partition function. Now, in our next discussion, we're going to use this specific formula, and we're going to see how we can, of course, incorporate the aspect of vibrational temperature in this case. And that's going to give us a final way of representing these specific aspects of a diatomic molecule as a harmonic oscillator in terms of a partition function. So catch us in our next video as we're going to look at the second aspect, and that's going to form our final bit and assist us understand, of course, the specific representation of this partition function, or rather harmonic oscillator in terms of energy, in terms of a partition function. So that is it for now, guys. By God bless you. Catch us in our next video.